is not only about reducing our emissions. And I don't think it's sustainable to ask that these sacrifices will be maintained forever. So fusion can be the solution that can allow us to move away from this sacrifice. It could be the sustainable solution for the future.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective on important societal issues.
Produced by Soapbox Media.
Hello and welcome to another episode of The Rational View. In this episode, I'm continuing my exploration of the state of nuclear fusion research. I'll be interviewing a leader in the MAST fusion experiment. MAST is an acronym for Mega Ampere Spherical Tokamak. A tokamak is a device that typically uses extremely strong magnetic fields to confine an energetic plasma and ram hydrogen nuclei together at high energies, essentially trying to replicate the processes occurring at the core of the sun to create fusion energy here on Earth. This process takes tremendous energy inputs and has been explored in the lab for decades without successfully transitioning to commercial power. Experiments are getting larger and larger and more expensive, and researchers have been making incremental progress towards the goal of break even. Join me as I explore the high-pressure science of fusion energy. If you like what you're hearing, please press like on your podcast app, send me a comment, share it with your friends. Love to hear from you. Fulvio Militello is a fusion scientist with 20 years of experience. Following a career as a theoretical plasma physicist and science manager, he is currently the director of Tokamak Science and MAST-U at United Kingdom Atomic Energy Authority. Before joining UK AEA, he worked in Italy, France, and United States in national laboratories and universities, authoring 100 scientific papers. Fulvio is also an adjunct professor of physics at the Chalmers University of Sweden and visiting reader at the Imperial College of London. While his heart is still in Italy, he lives in Didcot, UK, with his Swedish wife, met in France, and 2 daughters born in the UK. In his free time, he likes to cook, practice martial arts, read philosophy books, play games, look at the stars, and learn as much as he can about everything that stimulates his curiosity. Dr. Militello, welcome to The Rational View.
Thank you for having me.
You've got a very busy whiteboard in the background there. You're obviously working very hard at making fusion happen.
It's not just for decoration, but many people observe that this whiteboard is actually quite busy. I do use it.
Your bio is very interesting. What kind of games do you like to play?
Oh, I really like board games. I'm quite excited also about role-play games. There is, I got an inner child.
Ah, just like me. We're very similar that way. Tell me, why did you become interested in nuclear fusion?
Well, I mean, the story is quite interesting. It's actually by chance because originally I studied in Italy, in Turin, as an aerospace engineer. I really wanted to send things into space. But then during the course of my studies, I realized that I wanted to be a theoretical physicist. So I picked the subject that was closest to theoretical physics in my university, which was plasma physics. And I was very lucky to have a professor that was very interested in fusion and very well connected. And here I am.
You must like, have you ever seen the Big Bang Theory television show?
Oh, yes, of course.
Yeah, they got the physicists and the board games. It's very, very similar, I think.
Well, maybe I'm not that nerdy, but okay.
Could you introduce us a little bit to your group's approach to achieving nuclear fusion? What is MAST-U?
Yes. So first of all, we need to understand that there are different paths to fusion. And the path that we're following here at UKEA is the so-called magnetic fusion concept. And this consists in creating magnetic bottles, so to speak, that are of the shape of a donut, a torus in mathematical terms. And within this bottle, we try to create the conditions for fusion, which are substantially extremely large temperatures. When the fuel that we use, which is typically isotopes of hydrogen, and with isotopes I mean atoms that have a different number of neutrons, but they are the same element, they are still hydrogen. So these isotopes are colliding with each other when the temperature becomes very large, and these collisions eventually lead to a number of reactions, fusion reactions, that transform the hydrogen into helium, and by doing so they release quite a lot of energy. The logic here is that this magnetic bottle can confine very well the plasma that is so hot that would immediately cool off touching any other a solid surface. So we contain it using these magnetic fields. And this is one of the possible ways of doing fusion, and at the moment is one of the most successful.
So MAST is an acronym for mega Ampere spherical tokamak. So many people may be familiar with the image of a tokamak as a toroidal chamber which compresses the plasma using magnetic fields. You have a spherical tokamak. So this is a kind of something that would be odd to most people, and they say, what is this? Why do you use a spherical tokamak?
Well, this is actually just a geometry. It's nothing more complex than that. If you can imagine a standard tokamak as a donut, you can imagine a spherical tokamak as an apple without its core. So it's still geometrically a torus. It just has a different, we call it aspect ratio. So it's a little bit more compact than your standard donut. And it has a number of advantages. And the main one is the fact that we think that by using spherical tokamaks, we can use better the magnetic field in the device, and that makes the machine more economically convenient and more compact, which is actually something quite important when you're thinking of making fusion commercial, because the cost of a future power plant will be strongly related with the size of the power plant itself. The capital cost of a power plant is the bulk of the cost of electricity, substantially, for a concept like fusion.
Okay. So I've recently chatted with the folks at the U.S. National Ignition Facility who are doing laser fusion, maybe your competitors in a different sense. They've announced that they've achieved ignition. They've equaled the energy that they put in with the laser. Where are you at in your work, and how are you breaking even with your energy production?
Yeah, okay. So reaching ignition is a slightly different concept. Ignition is actually when you do not need to put any external energy into the device in order to get fusion. What we really want to get at the moment is to reach break-even, which basically means receiving from the fusion reactions as much energy as what we put in the device itself. The record at the moment is of the order of 0.67 in terms of the ratio between power in and power out. And this was achieved at JET in 1997. So it's been quite a while ago. And that is the record, of course, for magnetic fusion devices. My understanding is that NIF has a slightly higher number, but not significantly higher, around 0.7. Now, one thing that we need to understand is that at the moment we are not aiming with our experiment to go beyond that, and we cannot with the current devices. But ITER will go well beyond this value. This number, which we are citing now, is called the fusion gain factor, and one corresponds fundamentally to the amount of energy that we get out equal to the amount of energy that we put in. And ITER will reach Q equals to 10, so a factor much larger than what we can get from our experiments. And the reactor probably will have to go between 10 and 40.
Mm-hmm. So you mentioned ITER. Could you tell us all what the ITER is?
Yeah, ITER is a new experimental device being built at the moment in France, in southern France. It is a really large experiment that required the collaboration of a very large number of countries. It includes fundamentally countries that represent 2/3 of humanity. And just because of that is quite challenging, but also quite exciting. It is a tokamak. It is a conventional tokamak, so it looks like a donut, not like an apple without its core. It's not a spherical tokamak. Its goal is fundamentally to prove for the first time that we can go beyond Q equals to 1 with Q corresponding to this fusion gain factor, that we can receive from the plasma more energy than what we put in, and by a factor 10. It will be quite interesting because we will go in regimes where the plasma has never been. And we are all quite excited about that. And the fact that it's an international collaboration and that the whole world is united around it is also quite inspirational, in my opinion.
So your work at MAST is like a stepping stone towards this ITER challenge. Is that how you see your work? You're working towards this next big fusion reactor?
Partially. Let me elaborate a little bit on this question. In reality, the stepping stone is really JET, the other device that we host here in the UK. And JET is a standard tokamak that has produced the record fusion energy just last year. And as we were saying earlier, also the highest performance in terms of fusion gain in 1997. And JET is very, very similar to ITER in terms of internal plasma-facing components. So the parts of the device that are facing the plasma. And by design, we did that by design. It has also a lot of other features that are compatible with ITER, apart from the size. It is much smaller. Just to give you an idea, ITER is going to have a linear size of the order of 6 meters. This torus is going to be 6 meters in radius. JET is only 3, so it's roughly half of that size. And also the volume where the plasma is going to be contained is much smaller at JET than at ITER. ITER is going to be 800 meter cubed, while JET is going to be 100 meter cubed, so it's a factor 8. So apart from the size and also partially the power that we're going to inject in ITER, the two devices have a lot of similarities. Although ITER is definitely one order of magnitude more complex. All the systems that are required to make a machine this big are really much more complex than the current experiments that we have at the moment. So STEP is really the nearest neighbor to ITER. And it can also use the same fuel that ITER will use, which is deuterium and tritium. MAST has a different goal. At the moment, we do not really have power plant prototypes in the community. We have experimental devices. And each experimental device has to address a certain physics problem. Now, MAST Upgrade is designed to address a specific problem, which is understanding how to handle the power that the fusion reactions will generate inside the plasma, and make sure that they can be exhausted from the device in a safe way. Also, MAST has this different geometrical design. And it is, if you want, a test for potential spherical prototype power plants. So it's not going to go exactly in the same direction as ITER, but it can still give some useful information for ITER. But you have to imagine all the different fusion experiments at the moment as different tools, and we have in the community a toolbox, and we need to pick different ones to address specific problems. And while JET is the closest to ITER, we still need many other devices to address problems that will be very relevant for future power plants.
It's been said many times by various pundits looking at fusion energy that fusion practically is always 20 years away, and they've been saying this for over 50 years now. Are we making progress towards a goal? Where do you see the end line lying? Is ITER going to be the time when we demonstrate that we can make practical fusion energy a reality?
I was sure that you would ask this question. So there is a pretty elaborate answer to this question. First of all, I would like to cite a very famous Russian scientist that was asked the same question probably in the 70s, Lev Aristovich, and he was one of the fathers of the Tokamak concept that we are using in our research. And what he basically said was that fusion will arrive when the society will need it, probably we need to have a fusion now, considering the climate crisis and also the current situation with fossil fuels. So I think that it's also a request from the society that will make fusion happen. It's not only about the technical advances that you're doing, but the technical progress is significant. There is a parameter that can measure, one of many, but a significant one, that can measure the progress that we're doing. And this is called the confinement time. This is fundamentally the time it takes for the plasma to cool down if it's left without any heating source. So typically, in order to keep the plasma hot and generate the fusion reactions, we have to heat the plasma up. So if we let it cool down without any external source of heating, it will take a certain amount of time for it to cool down. And that is the confinement time. It's called confinement time. The longer this confinement time, the more efficient and the closer we will be to a working fusion power plant. And this quantity has followed for many years the Moore's law, the same law that the computers are following. So there's been a significant progress in this respect. What we now need really to tackle are the technological problems. We still have a little way to go for the physics, but we're getting there. And ITER definitely will be the first demonstrator of the feasibility of fusion as an energy source. And JET has already done quite a lot in this respect. But after that, we need to, and we're already actually working hard on the technology. We need to make sure that we have an efficient power plant, not only a power plant that is producing fusion. And that is, to a large extent, also a technological challenge. But we are already working on that systematically.
You say MAST is looking at how to handle the power of the fusion generator. How do you capture the energy of fusion and turn it into practical electricity, for example?
Yes. Let me explain also my previous statement. Whenever there is a fusion reaction based on deuterium and tritium, you end up having 80% of the energy contained in a neutron that is released, and it's a very energetic neutron. And capturing the energy of this neutron is what will then produce electricity. But 20% of the energy produced in the fusion reactions is released as alpha particles. Alpha particles are simply nuclei of helium. And they contain quite a lot of energy, which remains in the plasma, which is good because it keeps the plasma hot. So we need a little bit less external heating that needs to be powered by electricity. So having these alpha particles is good. But at the same time, part of this energy will go towards the internal part of the device that is facing the plasma. And just to give you an idea, the heat fluxes, the energy fluxes that this part of the machine will receive are a factor 1,000 higher than the heat fluxes that the shuttle re-entering the atmosphere was receiving. So they are incredibly large energy fluxes. But we are designing the device in such a way that these heat fluxes can be accommodated. But your question was, how do we extract electricity out of it? Well, we extract it by having these neutrons that are neutral particles, so they are not affected by the magnetic field, flying out of the device, so they are not confined by the magnetic bottle like the fuel is, and they are captured by structures that we call blankets. Now, these blankets have two purposes fundamentally. One is to receive the energy of the neutrons, and fundamentally heat up. And then there is a heat exchanger where typically a working fluid is flowing through, could be water. And then we produce steam, like in a standard power plant where you can burn coal or oil or gas. And then there is a turbine that is basically producing the electricity. So the key is to capture the energy of the neutron and to boil water, fundamentally. The second thing that the blankets are doing is to breed the tritium. Tritium is a substance, an element, that decays after 12 years. So it's not present in nature. We have to generate it. And the neutrons that will arrive in the blankets are fundamentally breaking lithium particles and transforming it into tritium that we then recirculate in the device and put inside the plasma as a fuel. So that's how it works.
Interesting. Very interesting. So
quite complex, right?
yeah. No, I mean, neutrons are obviously very difficult to stop because they have no charge. They just kind of go through everything, and they're not neutrinos. But so you have these heavy blankets that have lots of stuff in them, and they just kind of jostle about and heat up. Interesting.
Yes.
Interesting.
Yeah.
So
yes.
You kind of mentioned that you think we're at the point where most of the physics problems have been tackled, and we're looking at more of an engineering development to get to practical fusion. Do you see any showstoppers in the way between where you are now and practical fusion? Like, what physics? Is there any physics that lies in the way, or is it just let's build it and make it efficient?
No, of course we are not yet there. Also in terms of physics, we still need to understand a few things, but we have confidence that we can do that. And the recent experiments at JET have increased our confidence substantially, because we know that the only device that will be power plant relevant is a power plant. So the physics that we will have in the power plant will be to a certain extent unique, but we can predict it. We have tools to predict in advance how the plasma will behave inside the power plant. And for example, for a jet, we tried to simulate with numerical codes the behavior of the plasma in advance before the experiments. And those predictions were then confirmed by the experiments themselves. And something is happening also similar is happening also for MAST upgrade, where we predict a reduction of the energy density fluxes in our device towards the plasma-facing components, and this is actually happening quantitatively as we predicted. So we think that there are still unknowns in the physics in terms of the practical realization in our current devices, but we think that we can bridge the gap with our numerical tools and with our theories and with our modeling. It will still take effort, and we still need to validate and make sure that these tools are fit for purpose, but we do have confidence that this can happen. In general, I think that achieving fusion will require three things. Continuing doing experiments in devices like JET and in future like ITER, because asking Mother Nature whether our questions are answered the way we think is essential. We will also have to have very good numerical tools and modeling tools. So there is a very strong role for theory and modeling. And finally, we need to have people that have experience on how to operate these devices. It is crucial that we maintain expertise on how to operate fusion devices, because there is a lot of ingenuity going on and invention. It's a little bit like driving a car. You need to have good pilots, and this is a capability that we need to maintain. So it is not only about the physics itself; it's also about having the right people able to respond to things that perhaps are not completely well understood.
And like, how difficult? I mean, obviously, containing a plasma that's hotter than the core of the sun seems a difficult thing on the face of it. How difficult? What tricks do you use to keep that in there? I imagine it's like stuffing an octopus into a mesh bag.
It's a good analogy. Yeah, in reality, the plasma sometimes, especially for the physicist, does appear like a living thing that is reacting to what we're doing, that is changing also sometimes depending on its own will. We control it, obviously, so it's not like the plasma misbehaves systematically. We know how to treat it. Let's put it this way. But what do we do to maintain it where we want it to be? Well, the magnetic fusion concept is based on the fact that the plasma, which is fundamentally free electrons and free nuclei of hydrogen, typically, are electrical particles. So they have a charge. Having a charge, they respond to electromagnetic forces. And by creating a very intense magnetic field, and it is very intense, in our devices, we force the trajectories of these particles to follow certain paths, which are well contained within the device. So we make sure that using electromagnetic forces, the individual particles that make the plasma, and which is our fuel, follow lines that we want them to follow. That is never perfect, because obviously this is a thermodynamic system and there will be always losses, and it's a fact of nature. There is nothing we can do about that. But our effort is to control that as much as we can, and in particular to make sure that the mechanisms that are reducing the confinement time that we were discussing earlier, which are typically turbulent mechanisms. So there is turbulence in the plasma that is removing its energy quite efficiently. So reducing this turbulence is one of the things that we try to do, and by doing that, we will ensure that the confinement of the plasma is better. So how do we improve this? There is a lot of modeling going on, a lot of physical understanding on how we can make sure that the plasma behaves the way we want. It's definitely not trivial, because sometimes it really feels like a human body with many different internal organs that are behaving in synergy and in completely different ways. So there are many phenomena that are going on in the plasma. And we needed to tackle them all in a synergetic way, in an integrated way, in order to make sure that we can have a package that then is efficient and that is properly contained. But broadly speaking, we are also actively monitoring what is going on in the plasma, and we are also acting on the plasma itself by changing, for example, the magnetic fields, by changing how much fuel we inject in the plasma, by changing how much power we inject in the plasma, and by adapting like that, we control actively the plasma itself. You might have heard that now a number of research groups are also trying to apply artificial intelligence to this kind of control. So if you want, it's always a mix of designing the plasma in such a way that we can optimize its behavior, and then actively controlling it during the operations that we have when we do the actual experiments. And we do the same also for reactors, for power plants.
So you mentioned that the confinement time is increasing by Moore's law. What confinement time are you achieving right now? How long can you keep it?
Well, the confinement time in JET for the record-breaking experiment was of the order of half a second, roughly, and that's fine. That's something that is already this parameter is already sufficient to give a pretty decent performance. We aim, of course, to improve that always. the better the larger this number, the better is going to be the fusion performance. It's part of this fusion tripod product that is also used to understand the quality of fusion. The density times the temperatures times the confinement time. Magnetic fusion is focusing especially on the confinement time. It's the difference between inertial fusion and magnetic fusion. They have a very, very, very tiny confinement time, so orders of magnitude lower than ours, but they have very large density and temperatures. We have equally large temperatures, but much lower densities. And we make this up by having a larger confinement time.
Yeah, definitely many orders of magnitude. I think they were saying they're like, picoseconds of ignition time.
Correct.
Whereas you have
Correct.
half a second. So, 12 orders of magnitude between friends.
But you see, the difference here is that the pressure in inertial fusion is very, very large, much larger than the pressure inside the sun. Our pressure is basically 1 atmosphere. We do not have high pressures inside the device. The temperature is very high, but the density is very low. So the pressure is fundamentally the same pressure as the environment.
I just want to get a feel for it. Now, obviously this is a relatively safe way to make energy, but people might be afraid when you say you're making temperatures like the core of the sun in the system. What happens if you lose confinement? Does it vaporize the facility, or what? Or
No,
is this
not
something
really.
that nobody worries about?
No, I think that a good analogy for what a fusion power plant will be and what the experiments are now is like a match in a storm. We are basically trying to keep a match lit up in a storm. It's really difficult, and it's very easy to have the fire going, disappearing very quickly. So actually, we are really struggling to keep the temperature as high as we need it. As soon as we take away the external energy that we inject actively in the device, the temperature goes down very rapidly. It is a very safe way of handling the plasma itself, because we can control how to terminate the discharges. It's not as simple as I'm telling you, but in general, fusion is intrinsically safe in this respect. What can happen is that localized events, uncontrolled events, in our experimental devices, but not in future power plants. We are actively working to not have this in power plants. Might melt part of the device internally. And this can lead to the device stopping to work, and then significant repairs would need to be done. But part of the fusion program, research program, is to avoid these actively, and MAST-Upgrade is an example of why we are of how we're doing that. It is something that the fusion community is actively investigating, and we do have solutions that we think would be viable for power plants.
Very cool. So there seems to be these two very different approaches to getting fusion at the core of most of the physical work being done in labs these days. The National Ignition Facility and the Tokamak approach. Two huge teams, very well funded. Can you give me a trade-off of the pros and cons of the two approaches? Why do you think Tokamak is better for commercial approaches? Or do you have an opinion on which is the best approach?
Well, earlier you were saying that they were our competitors. I don't think that there are competitors in this field. We are all working for the same goal, which is actually a very noble goal of achieving fusion. So I think that at the moment nobody has bragging rights, and nobody can say this is going to be definitely the solution that we're going to have. Let me give you an analogy, if you want. 150 years ago, people were still looking, even more than that, we're still looking at the sky, and we're seeing birds flying, and we're saying, okay, we want to do that as well. Exactly like we see the sun in the sky, and we're thinking, yeah, we want to do we want to get the same physics on Earth. And the first attempts of flying were air balloons, and then zeppelins. and then airplanes. There were many different potential solutions to the same problem, and I think that also fusion might be the same. We might end up with many different approaches that might be equally viable. And at the moment, it's a bit too early to assess which one will be the winning one. And even the one that perhaps we will push forward first might not be the one that our grandchildren will see in the future. Exactly like we do not see air balloons flying in our skies. So let me tell you a little bit about the differences between the two approaches. As I was telling you earlier, in terms of physics, the difference is that they want to have very large pressures and they don't need to have very large confinement times, while we do exactly the opposite. And this drives the way we design our experiments. We want to have very efficient magnetic bottles. They want to have a very large bursts of pressure. And this is what makes the difference between the two schemes. But there are similarities as well. I was telling you earlier about the turbulence in the Tokamak, that is in the plasma, that is fundamentally removing very efficiently the energy in the plasma itself and cooling it down. Also, the inertial fusion community has similar problems. When they generate these very large pressures, Mother Nature doesn't like that. It doesn't like gradients. And this drives instabilities, which in a tokamak become turbulence. And in inertial confinement concept, they can generate a loss of efficiency. So this is in terms of physics. In terms of technology, both concepts use very large, they're big science. They require very large hardware to be delivered. Inertial fusion requires very large lasers. And we do need very large magnetic coils. For them, the challenge probably is to make sure that the targets that you're using are properly positioned, and there is a repetition of these reactions that is viable from a commercial point of view. For us, instead, is understanding how we can minimize the size of a device and make it commercially viable. These coils are massive. If you think about the ether coils, they have superconductive strands of a material that is called niobium 13, and they are 100,000 kilometers long. You could wrap the equator twice with all the strands that you have in the ether coils. So just to give you an idea of the magnitude of this. So the more compact and the simpler the device is, the better. And we are still trying to find solutions for that.
Yeah, no, the ignition facility, the lasers, like the hundreds of extremely high power, high cost lasers that they need to put together, it seems like a daunting task to build an operational system out of that. Personally, I think that the Tokamak is a simpler approach in terms of the technology that's involved in putting it together and making it work. So you're saying that you're using superconducting wire for your coils. There's also, I think, some people that are looking at going to permanent magnets. There's a lot of high quality rare earths coming out. Is there any particular breakthrough that's helped the most? Can you maybe talk a little bit more about which technologies breakthroughs have pushed us further the most in the Tokamak approach?
Well, I think that if you're talking about coils, at the moment, not all the coils are actually superconducting. JET has copper coils, and this is one of the reasons why we could not extend the duration of the record discharges for longer than 5 seconds. But new devices are typically being built with superconducting coils, like ITER, and having and this is if you want, it has a significant impact on the economy of a power plant, because it really allows us to have much longer discharges, much longer plasma, sustained plasmas, and this for us is really crucial. I think that the development of strong magnets that can lead to magnetic fields of the order of 20 Tesla, it is going to be quite important for the field. And there are recent breakthroughs also from private companies, for example, in the US, that have demonstrated real size coils for smaller experiments, but still coils that can reach this level of magnetic field. The larger, in general, the better in terms of fusion confinement. So this is one technological breakthrough. I fundamentally focused on the coils, but if you want, I can tell you also a little bit more about other breakthroughs that I think will be needed. One of them, for example, one of them is on how we heat up the plasma efficiently. As I was saying earlier, the plasma would cool down very rapidly if we were not heating it continuously, and we would not create the conditions for fusion. One thing that we are looking at the moment is how to do this in the most efficient way. There are a number of technologies that are available in our experiments at the moment, and they're pretty simple to explain. One of them is called neutral beam injection, and it's fundamentally based on the fact that we have particle accelerators that are launching very energetic neutral particles in the plasma, and fundamentally by friction, they are heating the plasma. These are maybe not the right solution for power plants, because they are extremely complex, they are extremely expensive, and they make the design of the power plants a little bit more complicated. We also have so-called resonant frequency heating, which is fundamentally very similar to what happens in a microwave oven, in a standard microwave oven. We have big antennas that are launching electromagnetic waves that resonate at certain spatial frequencies in the plasma, and they heat it up. And we think that strong resonant frequency heating in the future could really make a big difference in how the plasma will behave and in the efficiency of the reactions. It is something that we are actively studying.
You mentioned briefly on a commercial group in the US that there are a number of commercial groups around the world who are raising literally billions of dollars to build commercial fusion generators with great fanfare and great announcements. Would you invest your money in any of them?
Well, I think that these commercial companies are extremely interesting. Let me go back in time for a second. In the 1960s, we had a lot of ideas on how to develop fusion. And then there was also a graveyard of ideas that actually did not work. And it's still out there. But that time was very exciting. Then in the late 60s, the Tokamak concept became a little bit more prominent, given the results that the Russians achieved in their T3 Tokamak. And then the Tokamak became a little bit more mainstream as a concept. I feel like these private companies are now injecting new ideas in the community, some of which are not really mature, some others are more mature. But still, the fact that we have re-injected vitality and energy in the sector is absolutely positive. I do not know whether these companies will succeed or not. But as I was saying earlier, I don't think that anybody has at the moment bragging rights on fusion. Of course, there are concepts that are more mature. The Tokamak concept is been tested now for decades, and is the one that has produced probably the best results. But at the same time, I do not exclude that we might have different approaches out there. So yeah, I'm actually quite excited about the fact that these companies are out there.
Which is your favorite?
Oh, I don't think that I'm in a position to answer this. I mean, I could. I do have answer. I've answered in my mind, but I cannot really tell you. I think that my position does not allow me to do that. I think, I think that I'm quite excited about a number of them. They have good idea, good people, and I think that they can really help fusion move forward.
You know, you are kind of have your finger on the pulse, and really it is at the time where society does need fusion power. So going back to your quote from the Russian physicist, we do need it now. How long is it? Like what's the time frame, if you're a betting man, to say that we're going to see our first commercial fusion reactor go into service?
Yes. Okay. So generally speaking, in the community at the moment, there are two approaches, which include both private companies and national laboratories. There is an approach that I would define evidence-based, and another one that is schedule-based. So evidence-based path to fusion is fundamentally trying to use the current knowledge that we have acquired in our experimental devices over the course of many decades, and try to project it forward with relatively safe technologies, and we are relatively safe and safer from not from a risk point of view. Nothing is going to explode. It's about the possibility of these technologies to actually work reliably. And with our current physical understanding, this approach is followed by a number of laboratories, and it might lead to fusion perhaps in the 2050s, the first prototype power plant in the 2050s. Second half of the century, this is what, for example, the Eurofusion roadmap. Eurofusion is a big organization in Europe for fusion of national laboratories. It says the second half of the of the century, with a deployment on larger scale, perhaps towards the end of the century. There are then also schedule-driven approaches that are a little bit more ambitious and adventurous, trying to perhaps bet on technologies and on physics that that are not as mature, but where we have at least some confidence they might work, and they have a slightly faster pace that is substantially aiming at having prototype power plants around the 2040s, give or take. And this includes also what we are doing here in the UK with our STEP program, the design of a spherical power plant that should start operations around the 2040s. One thing that I want to say very clearly is that I'm not sure how much fusion can contribute to the climate crisis now, but there is a very important thing to understand. If we want to achieve net zero as soon as possible, we will need to ask mankind to do significant sacrifices. It's not only about reducing our emissions, and I don't think it's sustainable to ask that these sacrifices will be maintained forever. So fusion can be the solution that can allow us to move away from this sacrifice. Could be the sustainable solution for the future. And definitely, if we can in the second half of the century deploy a significant fleet of power plants, it will make a difference. My expectation is that we might have of the order of 10% of the world fusion energy production based on fusion towards the end of the century. But that doesn't seem large, but it's basically the whole Europe, if you're thinking about that. But the energy market is also going to be a question mark. It's very difficult to make prediction in this area.
Yes. Things are changing, and we're in a state of flux at the point that we're at.
Yeah, we're always definitely hoping for a breakthrough, but a power plant is a complex object. It will need time to be developed. But one thing that is making me confident is that now in the community, we do have a lot of attention on how to design and build a power plant. And we are thinking very carefully about that. We are thinking about what is needed. which kind of supply chain we will need, how to technologically engage companies, so that when we will be ready, we will be able to deliver that as quickly as possible.
That definitely is an argument for commercialization, to move into industry from the laboratory setting, because when you go from the physics problems to the engineering problems, then you need capital and you need speed, I think.
Most definitely, when you move to commercialization, you need partners that are industrial partners, because deploying to the scale we would like to deploy fusion requires people that have built things that are extremely large and extremely complex. And we have in the community, but a level of experiments. We need industrial capability as well.
Yeah, indeed. So this has been very helpful. I really appreciate you coming on the show and telling us all about your work in fusion and in MAST-U experiment. So thank you, Fulvio, for coming on the Rational View. For coming on, I'm going to send you one of these T-shirts so that you can show off to your friends. Yeah, it's a very high prestige to be on the Rational View. Before we go, I have one last question for you. So are you a player or a dungeon master?
It depends. I prefer dungeon master.
I thought so. With the management hat there, you have to control.
Yeah, you got me. Thank you very much, and thank you for having me.
Very good.
If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patron.podbean.com/therationalview. Thanks for listening.